You should have mentioned it a few minutes earlier.
Someone just put it on the chat just now.
I'm not reading the chat, so
Yeah,
you
that's
need
why I
to,
said something.
speak up. You need to speak up. So lesson learned. Okay, very fast electronic configuration and bonds. This is the exploded view of the atom of lithium. Central part is in black, 3 positive signs for 3 protons. Because lithium's atomic number is 3, it's got 3 electrons to deal with. 2 go in shell 1, 1 goes in shell 2. There is a core shell, the inner shell, and the outer shell is the valence shell. Valence shell is important because when 2 atoms, bond or make whatever kind of bond, a covalent bond by sharing or electron or ionic bond, they use their valence shell electrons. So valence shell electrons are important for, that's not 9, that's an O, for bonding. So shell 1 and shell 2, inner and outer. Outer is important, inner is not important when it comes to bonding. I'll pause for like 5 seconds. That's that. We're going to discuss at this point, we're going to continue to discuss electronic configuration and then slowly get into bonds. And then we started writing down some Lewis dot structures. Lewis dot structures are the representation of the elements or molecules using their letter acronyms, Li, H, C, whatever, and putting the number of dots as number of electrons in the valence shell, not core shell, not everything. This doesn't mean lithium's atomic number is 1. This means lithium has 1 valence shell electron. So that's what we have been discussing. Now we are writing down few electronic configurations. Hydrogen is 1s1, lithium is 1s2, 2s1, and we can also show it as this. Okay, and this is core, and this is valence. This is not important. Not important. This is very important. Okay, so we're going to just draw we're just going to draw for lithium the 2s level. We will at one point, maybe for the next few times, we're going to continue to draw everything, but get used to when I don't draw the inner shell, which is going to be the 1s. We're going to skip the inner shell. Okay, lithium. Let's do boron. Boron will be, let's do everything. 1s2, 2s2, 2p what? Borons? 1s2, 2s2, 2p?
1.
1.
1.
Very good. There is something funny that happens here. We'll talk about it in a second. Carbon is, this is not important. So I'm going to skip 1s for carbon. All I'm going to do is I'm going to do 2s and 2p. 1s2, 2s2, 1s2, 2s2, 2p2. Okay, I'm going to leave a little room down here. I should have done that for boron. This is 2s. I'm starting from 2s. I'm skipping 2p. I mean 1s. Sorry. Okay. Let me just draw one other element, nitrogen, which is 2s2, 2p3. Okay. Let's do that. So now, as you figured out, we will probably need some room here. Okay. And this is just another discussion that we did here. So I'm gonna kind of blocking them so that it's easier for you to see the different learning. Our target learning process right now, this exploded view and then Lewis dot structures. Okay, so let's write down a few more Lewis dot structures. Boron. Okay. Boron has 2 electrons in one orbital and 1 electron in another orbital. I know that many of you have already read the book or learned it already in the past. So, but just hold on, don't get too agitated that I'm dumbing things down. I'm dumbing it down for a reason. So I'm going to put boron, I'm going to show the Lewis dot structure of boron in 2 different ways. Either that, hold on, if you want to say something, okay? Or this way, okay? This or that. For carbon, the way it's written, 2 electrons in one orbital, this whole thing is valence. This whole thing is valence. So altogether, carbon has 4 electrons in the valence shell. So the way it's shown there, if I just exactly copy it from there, then 1 electron should be single, unpaired, another electron should be single, and there should be 1 pair. So that's one way we can represent carbon, Lewis dot structure. Or I know that you know the right answer, so just hold on. Or we can show it with 4 dots around the 4 quadrants, north, south, east, and west. We can show it that way. We're going to get to that in a second. Nitrogen is going to be easy. Up here, a single one here and a single one here and a single one here. Let's do oxygen. Even though we haven't shown it there, I think you guys can handle it. Oxygen, 1s2, 2. So this is 1s2, 2s2, 2p1, 1s2, 2s2, 2p2, 1s2, 2s2, 2p3, 1s2, 2s2, 2p, 1, 2, 3, 4, 5, 6, 1s2, 2s2, 2p4. Make sure that you're following up on the math. Fluorine, pair, 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 single. 1s2, 2s2, 2p, 1, 2, 3, 4, 5. Neon, pair, pair, pair. Everything is paired. Full octet. Okay? Everybody else is trying to be like him. We'll just do helium for the sake of it.
Isn't neon Ne?
What did I write? Oops. That's what you're supposed to do. That means you're awake and paying attention. That motivates me, what you just did. Thank you. Neon is not nitrogen. Thank you. Really appreciate it. I did do it deliberately, just to catch your attention. Sometimes I might do it, but I'm not doing it right now. Helium is 2, and since it only has level 1 electrons, 1 floor, so this is full too. Okay, not really octet full, but in its own little world, it's full. Okay, so now let's make some compounds very quickly. Okay, let's make compounds and show their. We're going to expand the Lewis dot. Let's expand the Lewis dot structure. This is the atoms. and this is going to be the molecules. Okay, we're going to expand it. So let's make a molecule with 2 hydrogens. Let's make the simplest molecule, hydrogen molecule. I hope I'm not dumbing things down too much because I know you guys already know it. The formula of that molecule, before we get to that point, let's write down another basic fact of bond. Okay, I need to kneel down. I need to kneel down in front of the goddess of what? Organic chemistry or bonds? A bond, a chemical bond, not James Bond. A chemical bond is made out of, it uses 2 electrons from either side. 2 electrons are involved from 2 atoms in the simple bond. Okay. So the bottom line is when you have a bond, either 2 electrons from this guy and this guy are being shared, or this electron from this element has been snatched by this guy. So this guy has 2 electrons now. The bottom line is whether it's ionic or covalent, 2 electrons are involved. I need one, and this guy has an extra, so an ionic bond happens, or I need one and this guy needs one, and so we share. So that's always the motivation. The bottom line is one bond always needs to start with 2 unpaired electrons, one here and one here, right? So unpaired electron can make a bond like a tentacle. I have a tentacle and then I'm picking up somebody else. A spider can pick up 4 insects, okay, because it's got 4 legs. So I don't think it can do that. You'll have to like go upside down, but that's a different discussion. Okay, so hydrogen, this guy has 1 electron, this guy has another electron. In order to make a hydrogen bond between two hydrogen atoms, this is atom and that's atom, hydrogen number 1 comes and shares with hydrogen number 2, and they have a chemical bond. This is a bond. And this bond is happening because hydrogen wants to look like helium. After hydrogen 1 has bonded with hydrogen 2, it has its own electron and it has access to a second electron. So it's kind of like, I want 20 bucks. I have only 10 bucks. My wife has 10 bucks. So we make a joint account with 10 bucks from me and 10 bucks from my wife, and we make a joint account with 20 bucks. I feel good that I have 20 bucks, just like the celebrities. Okay. So this guy thinks that it has access to 2 electrons and looking like helium, right? So that's that. So now, if hydrogen and carbon get together, based on this, so when it comes to making a molecule with carbon and hydrogen, if this were correct, the smallest hydrocarbon made from carbon and hydrogen, obviously you guys know the name of it, methane, would look like this, or the formula would have been CH2. If somehow that happens, I know you already know the answer. If that happens, then the formula of that molecule would be CH4. So if this is correct, if that's correct, then the formula of that molecule, the smallest hydrocarbon, would be CH4. Now, long time ago when this was not known, but chemists could still isolate methane. and then they could purify it, and they could basically do atomic analysis, or it's called elemental analysis. They could figure out that methane is made out of 1 part carbon and 4 parts hydrogen. Okay, they could figure it out by doing some combustion analysis. It's pretty cool. It's very old-fashioned, very antique methodology, but it's still used. It's kind of funny. It's kind of funny because when we submit a paper, manuscript for publication, certain publications which are very finicky and very high-end, they will want me to confirm that the compounds we have claimed to have made by doing elemental analysis, which is an ancient methodology. It's kind of like a very old tradition, like growing rice and picking rice and then getting the rice out of its husk, and it's ancient, right? It's been known to humankind for a long time. So elemental analysis is an ancient technology. It's still used, and sometimes I get frustrated because I have to pay for it. For each molecule, I may have to pay $25, and if there are 100 molecules in a publication, we are screwed. Okay, $2,500. That's a different story. So then we say, okay, we are not going to send the paper manuscript to this publication. We're going to send it to somebody else. But the bottom line is, scientists could figure out like whether methane is CH2 or CH4. Which one is correct? CH2 is correct or CH4 is correct? You guys know the answer.
CH4.
Yes. So this is wrong. This is right. If this is right, then this is right. If this is wrong, then this is wrong. If this is wrong, then this is wrong. If this is right, then this is right, right? So that's the bottom line. Similarly, it has been found out that when boron and hydrogen make a molecule, the smallest molecule containing boron and hydrogen is not BH, is BH3. So that molecule will look like the Lewis dot representation of methane is this. So I'm going to just write it down. Lewis dot rep. That's the Lewis dot rep of this. This is the Lewis dot representation of hydrogen. Lewis dot representation of boron is this. Okay, Lewis dot representation of the smallest compound made from nitrogen and hydrogen is this. It's pretty easy actually. I'm going to put cross as the electron from hydrogen. I sometimes use different shapes. You know what? Let's not put cross and confuse you. I'll just put like a circle. So that circle means it's the electron from hydrogen. Okay, oxygen. Pair, not pair, single. That means it can make a chemical bond by sharing with hydrogen. Okay, last, fluorine. I'm going to draw it upside down. HF, NH3, H2O, CH4, BH3. This is how you do the Lewis dot structure of molecules. You must show all the electrons. Okay, so for quiz 1, if I ask you to draw a Lewis dot representation of hydrogen, and if you do this, I take off point. If there are 3 points or 2 points for drawing the Lewis dot representation of hydrogen molecule, and this is what you do, you will get 2 out of 3 or 1 out of 2. Because you haven't, I know that you know the answer, but I need to know that you know the answer. You need to let me know very clearly that I know that each bond is made out of 2 electrons. One is coming from this guy, one is coming from that guy. So this is bad. Okay, so I'm just telling you what not to do. This is a bad way of showing Lewis dot representation of hydrogen molecule. Okay, I know the board is getting kind of crowded. What is good is this. Even if you do this, but you kind of cut it, that's good. Or if you show this, this is fantastic. This is great. The book sometimes does it in a slightly different way. If you're reading the book like vigorously, sometimes the book does it this way. I don't like it, but if you show your Lewis dot representation with the electrons kind of sandwiched between the two elements, I'm going to give you points. But I'll be very reluctantly will give you points very reluctantly. I will not like that answer. I will give you 3 out of 3. I'll say, I'll not check it off. I'll say, okay, 3 out of 3. Okay. I don't like it because it doesn't designate which electron is coming from where. I prefer my way. I prefer putting it on a line between the elements. And 1 dot here, 1 dot here. You don't have to use colors. You can use the same color. Okay. The board got extremely crowded. I think we need to lose some mass from here. So I'm going to take a snapshot. I'll give you guys like a few seconds. I have to stand right in front of the camera. So excuse me for doing that. I'm trying to be kind of vigilant. So take a look at the board and make sure you guys are on top of it. Very good. Simple stuff. This is something that you have already known. Electronic configuration, bonds, the exploded view, different levels. Core is not so important, but it's there. If I'm asking you about core shell and valence shell, you should know how to answer that. If I ask you to do an electronic configuration of some element, you should be able to figure it out. If I give you an electronic configuration, you need to figure out the element, you should be able to figure that out. I'm just saying these are the type of questions you might be expecting. I might ask you to draw Lewis dot structure of one of the elements. You should be able to do it. Remember, I might give you that, and I might say, what's the atomic number of nitrogen, oxygen, carbon, and boron? Don't be fooled. Don't say 3, 4, 6, and 7. That's wrong number. You need to add the core shell, which is not shown here. So it's 1 plus 2, 3, 3 plus 3, 6, 3 plus 2, 5,
Right.
4 plus 2, 6, 5 plus 2, 7, 8, 9, and 10. Okay, if you do the mental math, do not completely forget about the core shells when you are dealing with Lewis dot structure. That happens. Then we talked about Lewis dot structure of different molecules, and we kind of showed that. Okay. So far, so good. I'm not going to take any questions. This is still kind of review stuff. So I'm going to clean up the board, and I'm going to start discussing what happens with carbon and boron, and we'll go from there. Okay. So let me erase the board. How are we doing with time? 1 p.m. Okay, sounds good. Okay. I wish we had an electronic board that could basically capture the video, and that would be really nice someday. And I won't have to take snapshots for higher resolution pictures. I don't know if this technique, the technique that I'm adopting, standing in front of the board using the zoom camera, using zoom and using a web camera, it's going to be considered like antique someday. I don't know, maybe. Okay, board needs to be a little more clean. Give me a second. Hopefully this will bring more clarity. Okay, so I'm gonna kind of repeat what we just did. All right. So hydrogen is 1s1, only one orbital. This is the valence shell orbital. I'm going to just do a few more. Boron is 1s2, 1s, 2s, 2p. Okay. So again, this is not important. This is important. 2s and 2p because that's the number. That's the outermost shell. That's the valence shell. Okay. You already know that the molecule that boron and hydrogen make is not BH, it's BH3. We already know that. How? Well, if you take the molecule and analyze it by doing elemental analysis, you will figure it out that it's 1 part boron and 3 parts hydrogen. So this is not right. So the next, hypothesis and theories and hybridization theory and all these things happen, they're all based on results. You have result, you figured out that this is the molecule, this is the formula, and not this. This is not the composition of BH3 or whatever the compound is with the boron and hydrogen. Therefore, there is something going on here. So we say that this is the representation of boron in, I'm using smaller font. I'll tell you what I wrote, ground state. So when boron is actually in a molecule as contributing to the bond or bonds, 3 bonds with 3 hydrogens, we say that the boron goes to the excited state. When boron goes to the excited state, we put a star. Star means excited state. When boron goes to the excited state, what happens is something happens. In order to make 3 unpaired electrons, this is 2s and this is 2p, something happens. What happens? You need 3 unpaired electrons to make 3 bonds with 3 hydrogens. Unfortunately, this is useless. You only have 1 unpaired electron to make 1 bond with 1 hydrogen. Something has to happen before this can happen. What happens? You guys have no clue? How do you make 3 unpaired electrons from 1 pair and 1 single?
Having that hydrogen electron go into that orbital.
Very good. So this guy jumps here. I could have said that this is what happens, but I'm kind of trying to tell you the storyline that because that's the case, if we had found molecules such as BH, 1 hydrogen and 1 boron, when you do the elemental analysis, you find 50% hydrogen and 50% boron, then we would not have said that this is what happens right before boron makes a molecule with 3 hydrogens. Then you would have said, this is it, that's it. 1 pair and 1 single electron, and you get that guy, okay? That would lead to that molecule, okay? So this must be happening to let this sort of BH3 happen. You need 3 unpaired electrons, okay? So this is called the excited state. Same thing happens with carbon. Carbon is, I'm skipping core shell. Carbon is this. You know that that's not the case because the real carbon in a hydrocarbon looks like this. 4 hydrogens and 1 carbon. It's 1 part carbon and 4 parts hydrogen. That means this is the ground state. This is how maybe carbon is born. But this would lead to a wrong molecule, CH2. So something happens, it goes to the excited state, and it looks like this. As you said, answered in the previous situation, 2s and 2p. Now this carbon has 4 unpaired electrons. This is totally doable. Sorry, the dots kind of are too small. I was lazy. Okay, so remember the ground state and the excited state, it's important. Okay, take 10-second break. So ground state and excited state. Now, I'm going to bring in the next concept to you guys today, which is very, very, very important. Okay, before we do that, let's talk about the shapes. I hate to do this. Let's talk about the shapes of orbitals. It's a sketchy discussion. I'm very uncomfortable. Because they're all mathematical equations, so we can talk about S and P, but then D and F, good luck to you. Don't try to imagine. Okay, when we talk about the shape of orbitals, try not to stretch your imagination too far, and don't fall in love with the shapes of the orbitals. Okay, just take it with a pinch of salt that it's a little iffy situation. So let's get over this discussion. Shape of orbitals. That's my face. Even though I'm smiling, I'm not happy. Okay. As we described as X, Y, and Z coordinates, I'm just going to draw like 3 coordinates. X, okay, parallel, like this. Y coming toward you, and Z going up. Okay, it's basically like this. That's X, that's Y, and this is, okay. Old days, the cobblers used to use a tool like this. X parallel to the board, Y coming toward you, and Z up and down. Okay. S orbital is sphere, like this. What color shall I use? What color did we use for S orbital? You know what? Let's keep it because I need the other colors, blue, green, and let's use black. Okay, this is an S orbital. One S, let's say. 1s is going to be smaller, 2s is going to be bigger. The p orbitals, I'm sure you guys have already seen it, is a lobe along the x-axis, a plus lobe and a minus lobe. This is px. One lobe that way and one lobe that way. That's where the electron has been found to be concentrated in. So you can also like not think about it as a particle theory, but as a wave theory. The probability of finding the electron in the px orbital is here, like a little dumbbell, and the other side of the dumbbell. Okay, py is along y-axis, a dumbbell toward you and a dumbbell toward me, away from you, okay? This is Py, and Pz is up and down. Okay, that's 1s, that's, well, 2py, 2pz, 2py, and 2px, and obviously the 2x will be bigger, 2s will be bigger. It's going to be a larger sphere. 1s smaller and a 2s orbital will be larger. Okay, so this is how the shapes are. Do not ask me anything about the shapes of the orbitals, because you cannot really imagine how these orbitals will play along in the levels, right? You cannot imagine them in the outermost shell, like shell 2. How can you have those shapes embedded in that spherical shape? It just doesn't make any sense. So it's all abstract. Okay. Here is the bottom line. Here is the bottom line. Now let's start talking about the properties of the bonds. Okay, let's look at methane. Let's look at methane, and if this is okay, I'll cut the chase and I'll tell you like where our discussion is going. We are going to start discussing hybridization right now. Okay, pretty soon. We are getting into hybridization, and I'm setting up the stage right now. Like, what's the problem with this model? What is the problem with the model that we have to bring in another concept called hybridization? There is a problem with this model. Okay, the problem is this orbital X, Y, and Z, right? This orbital looks like this. These orbitals, okay, they are longer and larger, and this is smaller. Got it? Take a look, and you really need to focus right now. Don't play with your cat or watch YouTube if you're doing that. Those of you who have your cameras on, you're not doing it. But those of you who don't have a legitimate reason to turn on your camera, keep your camera off. And if you're playing or distracted, try to focus right now, because this is a constant source of agony and pain among you guys. First part organic chemistry lecture students. This doesn't sit very well. So please pay attention. When methane is happening, right? A carbon is binding with 4 hydrogens, right? The 4 electrons, electron 1, 2, 3, and 4, they're coming from 4 different orbitals. You know what? Let's do this. I think that'll probably make it more interesting. Let's use the color coding. Let's keep the s orbital black and change the color of these electrons. I think that'll be good. So a px orbital, 2px, 2py, and 2pz. Okay? There is an electron here. There is an electron here. The jump happened. It has an electron, 2px, already there. 2py, there is an electron there. And 2pz, now there is a 2pz electron. Right after the black electron jumps here, it turns red because it's sitting in 2pz orbital. Now let's change the color of the bonds, of the electrons. Okay, So there are 4 hydrogens. So it's using an electron from 2s orbital and an electron from 1s orbital of hydrogen, 1s electron from hydrogen, 1s and 1s. They're not changing. They're all coming from, they're all sitting in the 1s orbital of hydrogen. This electron is in a p orbital. It's kind of longish. This electron is sitting in a py orbital. It's kind of longish. The shape of that orbital is kind of longish and bigger. This electron is sitting in an orbital like that. So that's one bond. This is one bond. This is one bond. And this is the 4th bond. This is 2s. This is 2px. This is 2py. And this is 2pz. Let's start talking about bond lengths. If this is the case, if this is it, nothing else happens. Do you expect, listen to the question very carefully. This is something that you might be expecting in quiz 1 and subsequent exams. Do you expect all the 4 CH bonds to be off? Don't tell me if you already know the answer. Based on what we have learned, don't jump. Just pretend to be not that intelligent. If you have read the book, if you know the answer, don't answer that answer. Answer the question based on what we have discussed so far. This is what it looks like. Electronic configuration. 1 is in 1s, 2s, and 3 are in p orbitals. Do you expect the 4 CH bonds to be identical or different? 2 large, 2 small, 1 large, 3 small, or sounds like an order. I'm very hungry. I haven't had lunch yet. Or 1 small, 3 large. So the answer is 4 CH bonds. Okay. Question answer A. I'm not going to put the right answer. You know that these are wrong answers. 2 large, 2 small. B, 1 large, 3 small. Or C, 1 small, 3 large. What's the right answer based on what we have learned so far? Even if you don't think any of them is the right answer, which one is the correct answer based on what we have, how far science has progressed so far in our class?
A 1 small, 3 large.
So this is your answer. Anybody else wants to chime in? Or you guys agree? If you guys agree, can you just say yes or no?
Yes, I agree.
Yes, I agree.
Yes, I agree.
Okay, sounds good. Anybody wants to kind of just very quickly explain why this is the right answer based on what you have learned so far? It's simple, right? Tell me what you see.
The 2s orbital is smaller, and then the 2p orbitals are longer and larger.
There you go. So if this is correct, this is how methane should look like. If this is correct, then this is correct. If this is correct, then this is correct. But you know the right answer. So this is expected. This is expected. Do you think that's how methane bonds are, or there is something wrong with this? There is an anomaly with that. And in real life, the 4 bonds are not this way. How are the real 4 bonds? What's your prediction if you don't know the answer? Do you really think one bond is smaller and three bonds are larger, or do you think that they're all same length?
They're probably all the same length.
They're all the same length.
That's a good gut feeling. That's the right answer. So in real life, again, scientists could figure that out by doing some studies. All the four hydrogens are bonded equally and in a very uniform way. Okay, so this is wrong. This is wrong. This is how science progresses. So what we know now could be full of baloney. And people in the future, scientists will figure out that we used to be at the primitive scientists in 2021, and we didn't know anything any better. But this is how it progresses. Come on, we started out with horses and donkeys and bullock carts and horse-driven carriages, ice engines, electric cars. Who knows what's going to happen in the future, right? So if that's the case, then this is also not right. It's actually, in reality, that's not right. Of course, this is not right. This is not right. So there is something sketchy about this business. Okay? Take a look at the board, stare at it for maybe 30 seconds. This is where confusion happens, contradiction happens, and you guys get really all over the place. So I'm going to give you 30 seconds to kind of make sure that you guys are following everything. I'm sorry, excuse me for blocking the camera. This is picture number 2 for today. Take a look at the board and make sure you are following the consequences. I mean, the sequential learning, the concepts. Pretty straightforward so far. I'm going to erase maybe part of the board. I'm going to keep the left side. I'll keep my mouth shut for 15 more seconds. I haven't actually kept it shut for any time. Okay. All right. So this is how the orbitals look like. This is how the molecule method could have looked like if that were the case, but something else happens. So that the molecule is uniform, right? So let me erase. Just keep the carbon and hydrogen. You know what? Let me just erase everything and redraw so that you guys have a fresh outlook toward the board, so that we are not kind of dragging anything from the past. I've been trying not to drag things from the past, but we are all humans, so we keep doing that and suffer sometimes. Not all memories are perfect, right? Some memories are not good. I wish we could selectively erase some memories. Okay, so as bonding is taking place between hydrogen and carbon, let's quickly review what we have done so far. Okay, hydrogen 1s1 or this, only one shell. That's it. That's the deal. Carbon is a different story. 1s2, 2s2, 2p2. This is what it looks like. I'm just going to draw everything. But sometimes I may not draw the core shell. 2s2. I'm not using color coding because it takes up a lot of time. 2p. This is the ground state, GS. Okay. It goes to the excited state. And then something happens. 1s2, 2s1, 2p3. This is important. I might ask you some questions about this on the quiz. This is how you write it. And in picture, this is again, this is core. We don't care. We care about this because that's the happening place. Px, Py, Pc, they're all two, right? So the bottom line is, if that's the case, if this is the case, then the structure of the molecule will look like this. This is not, by the way, this is not Lewis dot structure. I'm just trying to give them some shape. Okay, long bond and a short bond. Okay, so then we know not correct. What is correct? This is correct. Equal. Equal length. Okay, so what do? Chemists go back to their drawing boards, start scratching their hair, the back of the scalp, start losing hair, and get frustrated and agitated and start infighting. Like, you don't know anything, then he says, you don't know anything, you know, the fight continues, and eventually someone comes up with a hypothesis. He goes, well, you know, I think this is what happens. Something happens between the orbitals and they mix. They mix and produce 4 identical orbitals. That's the only way you can explain it. So this is not how carbon is looking like when it's making bonds with other people, other elements. So it must be undergoing some kind of mixing. And that mixing is nothing but hybridization. Hybridization is a mouthful of word, but don't be intimidated by the word hybridization. Think mixing. You're putting 1 part of chili, 1 part of beef, and 3 parts of beans to make 4 parts of chili, identical chili. That's it, okay? Because you need to feed 4 kids and they want identical food. So what happens? This definitely doesn't explain that. We need to change our understanding of electronic configuration. So something happens. So this guy, I'm going to use the word mixing. It mixes or hybridizes. Hybridization. Hybridization means nothing. You put 1 S and 3 P's in the blender, you blend for like 10 seconds and pull it out and pour it in 4 orbitals, they look identical. That's it. That's all. It's pretty straightforward. So after hybridization, we don't draw them like this anymore. Hybridization has happened now. Then what do we get out of this mixing process? 1 orbital. You know, energy, as I said, energy is always written up and like with an arrow along the z-axis. If I draw something down here, that means 2s has less energy, 2p has more energy. 1s has less energy, 2s has more energy. So what I'm going to do is I'm going to try to draw the 4 mixed orbitals at the same level. That means they have identical shape, identical other properties, identical energy. Everything is identical. And this process is called hybridization. After hybridization, each orbital is a hybrid orbital. And how do you name the orbital? You count the number, what went into the blender. How many parts of beef and how many parts of bean has gone into the blender. We have thrown in 1 S and 3 P's. Everything went into the blender, whatever you have in the second level. 1s and 3p's. Therefore, it is called sp3 hybridization. This process is called, in this particular case, it's called sp3 hybridization. This is an sp3 hybrid orbital. This is an sp3 hybrid orbital. This is an sp3 hybrid orbital. And this is also an sp3 hybrid orbital. After they make the bond in CH4, when CH4 happens, carbon and 4 hydrogens, okay, in the molecule, this is what it looks like. This is from carbon. This is from carbon. This is from carbon. This is from carbon. So this is CH4, the 4 CH bonds at this point. Identical bonds. And this electron is from hydrogen, paired. This electron is from hydrogen. This electron is from the 3rd hydrogen. This electron is from the 4th hydrogen. And you can circle them. So this is a CH bond. This is a CH bond. This is a CH bond. And this is a CH bond. So I'm going to just redraw the molecule using the purple color. This is sp3, 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 hydrogen, 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 and hydrogen. That's 1s, that's 1s, that's 1s, and that's 1s. And all the bonds are identical to each other. This molecule is super uniform and perfectly identical size of the CH bonds. Let's take like maybe a few seconds break. I'm not going to take a picture yet. Okay. Ground state, excited state, hybridized state. We don't put the boxes because we draw like 4 lines. 4 lines means they're hybrid, they're mixed. It's not beef and beans anymore. This is the beef and that's the bean. This is the chili, identical, and the 4 kids are happy. They get identical food with each other. They don't fight with each other. Okay. Tell me if anything is bothering you at this point. This is a concept that doesn't sit well. It's kind of volatile. It sublimes away. So you guys really need to get it, because if you don't get it, it's going to haunt you through this semester and next semester when you take 128B. It's not that difficult. Are we okay or are we not okay? What does this silence mean? Can someone say that you're fine, feeling fine? You're not nauseated or having headache?
I think I'm good.
You're good? Sounds good. Thank you. Appreciate it. Anybody else? You're okay? You're following it? Any concerns? Right, Samantha?
Yeah.
Okay. All right. So hybridization happens. Carbon makes 4 identical bonds. And now let's talk about something else. So now carbon, this is a time when you need to start thinking if you should invest in a model set, not train, but molecular model set. Okay. So now you have 4 hybrid orbitals. Imagine, do I have purple? What happened to on my models? Somebody stole it. I don't have 4 purple ones. I have 4 blue. You know what? Let me use the blue. They kind of show up, right? So let's say there are four orbitals hanging off of carbon. Okay. I'm going to talk a little bit about the shape of this molecule. Four sp3 orbitals from carbon. That's the carbon. Okay. And what happens is when you have, now we are talking about bond properties. Okay. We talked about hybridization, the mechanism. Now we are talking about properties of bond or bonds. Okay. You got 4 bonds. In the middle, you have carbon, and you have 4 bonds. The bonds could be this way, or they could be flat. They could be planar, but they're 90 degrees apart. Okay. They could be like looking like an octopus. And the bottom line is, I need to introduce some concept here. They're like magnets. They're like magnet. There's a lot of electron happening here. There is electron here, electron here, electron here. There is actually a pair of electrons. There is a pair of electrons. Okay, and pair of electrons are repelling each other. There is tremendous repulsion. Repulsion here, repulsion here, repulsion here. That's called electron pair repulsion. You know what a really great metaphor is? Think about 4 bar magnets. You have played with magnets, right? You may have played with discs, but just think about a magnet. You know what? Let me use this. Imagine this is a magnet. You hang it, it's a bar magnet, north and south. Let's say that's the south direction. So when you hang it with a piece of thread, it'll always line up north facing south and south facing north. Okay. Let's say they're all north and south, north and south, north and south, and north and south. If you could put, I guarantee that somebody has figured it out and made up a toy like this. If you could put the 4 bar magnets with some kind of fulcrum, like where they're flexible and that thing can change direction. If you could stick it to the central part, okay, and if you could put them together with all of the north faces joined together here, and that's south, 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 and south, they're going to repel each other. You can do an experiment, and it'll tell you exactly what will be the shape of methane molecule. Okay, I'll tell you what the shape will be. Has anyone read or remember from the past? It's a T word. It's a long T word.
Tetrahedral?
Tetrahedral. Harpreet, thank you. So when you put 4 bar magnets with 4 connected to the same pole in the center, they try to stay away from each other as far away as possible. I used to use a metaphor, but my SI leader for this class, Isha, keeps mocking me. So I'm not going to use it anymore. I've become a little more sensitive. Now she's going to feel bad. She's a very sensitive person. By the way, does anybody know that your SI leader is going to UC Davis for tech school? I'm very proud of her. So when you see her, you can congratulate her. Like, we might have talked about it earlier. So north, south, north, south, and north, south, they're farthest away from each other. And this particular shape is called tetrahedral. Okay, they take up the shape. It's not flat. It's not like this. It's not 90 degrees. It's not a flat molecule with 90 degrees. That's wrong. It takes up a shape. Its shape is called tetrahedral. Okay, that's the shape. I think I'm going to discuss it on Thursday. and you can start Googling what tetrahedral looks like. I would recommend you start doing some homework because there is a quiz on Tuesday of next week, a week from today. Okay. I haven't figured out exactly how I'm going to administer it, whether it's going to be all free response. I should have graded your first practice quiz. I haven't done that. That's my plan for the week. I'm pretty much done with all my grant submissions. I have submitted 4 grants in like month and few days. So I'm really, I felt kind of burnt out yesterday for the last few days. I was also out of town. That's my excuse. So I'll start grading them, and we will discuss the quiz maybe a little bit more on Thursday. I would not mind taking a few questions from you from the homework on Thursday to dedicate the last 10-15 minutes. Okay, I'm going to take a picture. I'll make the video available as soon as I can, and see you guys Thursday. Okay, I'll block the webcam one more time. Just beg your pardon. I'll make them available as soon as I can. Okay. You know that I'm available during office hours, but you need to reach out to me first before I can set up a Zoom meeting with you guys. And I don't mind setting up Zoom meetings at other times. Please reach out to me. It doesn't mean anything bad that you're not intelligent or you're kissing up to me. That's what our son thinks. That seeing a professor means he's kissing up to everybody. He's kind of out there somewhere else in a different world. Sometimes we think that he's an alien. That's kind of rude, but he's interesting guy. So don't think like our son. Please email me and we can set up a time. Okay. Have a good day, people.
You too. Bye-bye.
Take care. Bye.
Thank you.
Sorry, I didn't even read the text. In the chat.
Well, it's just one person.
Okay.
Bye-bye.
Bye. Have a good one.